Today we will study circular motion. Whenever a body moves in a circular path, we call its motion as circular motion. Let's say this is a particle P which goes in a circular path, goes to P dash, and it covers an angle theta. The particle is said to be going in a circular motion. In a circular path, we define certain terms. One is called omega, is the angular velocity. It is defined as radians per second, and this is all equal to rate of change of angle swept. Similarly, there is another term called alpha, which is called angular acceleration, which is equal to rate of change of angular velocity. Now, for circular motion, the laws of circular motion, the equations involved are very, very similar to what we have seen in linear motion. For example, theta is defined as you remember from the linear motion situation, this was S, this was U, this was A. Yeah. Similarly, omega is equal to omega naught plus these equations are very, very similar to what we saw in linear motion, right? Here, this is omega at initial value, at initial time. This is final omega. From geometry, we can make out. Now, when a particle is moving from one point to another point, it has got a linear velocity which is tangential to the point where it is. If it is here, the tangential velocity will be always tangential to the path, or it will make a 90-degree angle with radius. And geometrically we can see is velocity is equal to r. R is the radius of the path into omega, angular velocity. V is the linear velocity at any time, like here. R is the radius, this radius. Omega is the angular velocity at that time. So we can see V is equal to R omega. This is the angular velocity. This is the linear velocity. And if we differentiate, dv by dt is equal to the radius being constant is also equal to r by dt. Now for a uniform circular motion, a particle is moving in a perfect circle with a constant velocity. The magnitude of velocity is constant, whereas its direction is changing at every point, which is tangential to velocity. In case of uniform circular motion, radial acceleration is equal to v square by r, where r is the radius of circular path and v is the linear velocity. If that is the case, then acceleration is given by this, and the direction of acceleration is towards center, meaning thereby a body rotating in a uniform circular motion with velocity v, radius r, will have an acceleration equal to v square by r, and its direction will be towards the center. So we can write force is always equal to mass into acceleration is equal to mass into acceleration. We have already seen is v square by r. So if a body has a mass m, it will be exerting a force F towards center. Now this force which is being exerted towards center is called centripetal force. It is this force which makes body go in a circle. For non-uniform if the circular motion is not uniform, meaning thereby the velocity at any time may not be same. Okay? Then what happens? In such case, there are two accelerations. One is radial, which is equal to v square by r. Again, this is directed towards center. And since this velocity v is not uniform, it can have an acceleration. And since the velocity is in tangential direction, acceleration will also be in tangential direction. So we call tangential acceleration which is same as dq by dt. And this will always be tangential to radial path or circular path. Meaning thereby it will be perpendicular to radius. You might have noticed if you're driving and if the path or the road is circular, the surface of the road is not horizontal. The road is slightly tilted, which is called banking. Meaning thereby, if you are not going on a circular path, the road will look like this. But if you are going on a circular path, the road will be something like this. It will not be so steep, but I'm just showing it for the sake of magnification. And this is how you will be driving. This is your car. You're driving like this on a slope. There will be angle between horizontal and the road. This phenomena of making roads tilt is called banking of road. Now, why do we do it? Let's see it. If you are going on a flat road, and you are going on a circular path, and the road is absolutely flat, what happens is, due to centrifugal force will act on you to push you outwards. For a while, this outward force is countered by the friction of your tires and the road, and you don't slip. But if your velocity becomes high, then this centrifugal force mv square, which is equal to mv square by r, where r is the radius of the road, circular road, m is your weight of the body, and v is the tangential velocity with which you are traveling. Now, if your centrifugal force which is trying to throw you away from the center or skid you away from the center doesn't happen so long as it is countered by friction. But there may be a time when your velocity is high and this friction, which were not letting you skid, may be overcome by this force. And if that happens, you start skidding. And obviously, you don't want this to happen while you are driving. Now, what is the way to avoid it? The way to avoid it is provide banking of road. Let's see how it works. In case there is no banking, the force that is trying to throw you out is this F, centrifugal force, which is equal to mv square by r. And there is a counter force which is acting to save you, which is called frictional force, which we know mu times n. And since the whole body is horizontal, so nu becomes mg. So this is one force, this is another force. So long as this force is less than this force, there will be no skidding, till they become equal, which means this is the end point. If you increase your velocity even slightly more, you'll start skidding because this frictional force will not save you. So for non-banked road, the highest velocity you can go is or now let's first explain what this diagram is all about. This is a horizontal position. This is the road which is banked at angle at angle theta. Now, this is your car which you are driving. It is as if it is coming out of the paper, so that you can get a perspective how the road is and how the car, what is the position of the car. The car seems to be coming out of the paper plane. Okay. Now, since this is the road, there is a normal force which will be acting perpendicular to the road, perpendicular to the surface, and they will be when this is rotating with a high speed, the centrifugal force will tend to push through the car outwards. That means it will try to throw the car in this direction. Yeah. But if it starts to throw car in this direction, there's a frictional force which will act opposite to it, and it will oppose it. So this frictional force will try to avoid your skidding, that means going outwards. Okay. Now let's do some analysis. This is the friction force F. We resolved into two components. One is F cos theta, since this is theta. This is theta, so this will also be theta. And another component perpendicular to is F sin theta. Similarly, this normal we resolve into two components, a vertical component which is n cos theta, and a horizontal component n sin theta, right? Because of centrifugal force, there will be force acting in this direction, which will be mv square by r, where v is the velocity, linear tangential velocity of the moving car, and r is the radius of the road, circular road. Now let's start making some equation. First thing is, let's compare equation in vertical direction, which is n cos theta is equal to mg this plus f sin theta. F sin theta is the resolved component of frictional force, which is acting down the slope. Because the why it is acting down the slope is because the centrifugal force is trying to push the car in the upward direction. So friction force always acts in direction opposite to the motion of the body. Okay, so this is our first equation. Then the second equation, if we take the horizontal components, which is n sin theta plus f cos theta, this is equal to mv square by r. These are the horizontal components. These are the vertical components. We know that frictional force should be less than or equal to mu times. If this is the case, no skidding will take place. Okay. So our frictional force will always be mu n. We don't know the value of n yet. So from these two equations A and B, what we can get is n cos theta is equal to mg plus mu n sin theta. N sin theta plus mu n cos theta is equal to mv square by r. Let me say this is equation C. Then from this equation, what we can get is n is equal to mg by and then by doing mathematical manipulation, we'll get mg sin theta plus mu cos theta divided by cos theta minus mu sin theta equal to mv square by r. Or Now, we have taken the condition that we took this condition. This condition means friction force is being applied is maximum. When friction force applied is maximum, this velocity is the maximum velocity that we can get. We can go to without skidding. So this velocity becomes our Vmax. Or we can write Vmax equal to RG whole another root. The maximum velocity that a vehicle can attain without skidding. Skidding in which direction? Skidding in this direction. Why? Because when the centrifugal force keep becoming more and more, it tries to push the car in upward direction. Now take another situation. Let us say, for example, if this car comes to a rest, what may happen? If the frictional force is too low, it can start skidding down on its own. Or if the velocity is too low, same thing can happen. Because in that case, the frictional force is not enough, or rather this mv square by r, which tries to push it this way, this upwards, is not sufficient to prevent it from going down. Okay. In that case, what will happen? Which way the frictional force will act? Since the body is trying to come this way, frictional force will act upwards in opposite direction. Now, if we do the treatment of all these equations, what we can do is everything will remain same since the direction of friction was changed. If we change the sign of mu, we will get the answer of our minimum velocity, which will be minus mu. This will be our minimum velocity. If we make our velocity less than this, then what may happen? The car, instead of skidding upwards, will start going down the slope. So we make sure these two formulas tells us that our velocity should be somewhere in between these two. There is another very peculiar phenomena related to circular motion. We have our Earth here, yes, and let us say there is a point P here. Now, since the Earth is rotating, will it have any effect on apparent gravitational force? Why? Why should it change? Yes, it can change because, as we have seen earlier, in a rotating body, in a uniform motion, there is always a centrifugal force acting radially outwards, centrifugal force which is actually a pseudo force, which is acting outwards. And the magnitude of this centrifugal force will not be same everywhere, because radius is changing everywhere. This angle theta is changing everywhere. Okay, so let's analyze it. Let's say there is a particle P which is making angle theta with the vertical. If this is making an angle theta, then we can say G dash, apparent G dash that we experience is G square minus omega square R, omega square R, sin square theta 2G omega minus R. This is the formula, wherein this is a standard G, which doesn't change with position of the Earth or rotation. Omega is the angular speed at which the Earth is rotating. This one. Rather, if you see it like this, it will be rotating like this. Then theta is this angle. So apparent gravitational pull is given by this formula, which it says that this will depend on our theta, the angle which it makes with the vertical, and omega. Omega we can consider to be constant. So theta is the only variable, which means we have some special, let's see some special case, and theta is 0. At poles, theta is 0, because you will be here. So the angle from the vertical is 0. If that is the case, then you will be left with G dash is equal to G square. This whole term will become 0. Meaning thereby, at pole you will have no effect. The apparent G will be same as actual G. Let's take another case. What happens at equator? At equator, theta will be 90 degrees, because in that case, you will be somewhere here, and this theta will be 90. If theta is 90, then we know G dash will be G square minus omega square R. Sin square theta will become 1. And this will be equal to G minus omega square R. So apparent gravitational pull will be less at equators. compared to standard G.